The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
For number 4, we have a thin film interference problem. So you have an equation that helps you with this type of problem. So let me write that down real quick. So our equation is 2t equals m plus 1/2 lambda n. So first of all, let's define these variables. M is of course the order number, as we've dealt with in many of the problems in this section, so that can be an integer. Actually, in this case, it needs to be a positive integer. A non-negative integer. It can be 0, 0, 1, 2, 3, on and on and on. So T is the thickness of the film, and lambda sub n is the wavelength of your wave when it's in the film. So in this problem, we're going from air to some thin film of oil with an n of 1.5. The information that it's on the surface of a clear pond with that n is actually unimportant to this problem, because all we're concerned about is what happens when the wave comes through here. Part of it is reflected, part of it goes through, and then comes back out. And we want those two pieces to have constructive interference. So right here, this equation is what gives you construction interference in a thin film. So I'll also try to explain it just logically, but let's solve for this. So first what we need to find is, and in this case we want the minimum thickness. So what that should tell you is that we want the m equals 0 case, the smallest one that we could possibly have. So what we need here, and we're trying to find the thickness, so we really just have this now. 2t equals 1/2 lambda n. So lambda n is the wavelength in this medium. So the wavelength of the light was 600 nanometers to start with. So remember that when you have a medium that has an n something other than 1, the wavelength just gets divided by that. So lambda n is 600 nanometers divided by 1.5, your index of refraction for the oil. So this gives you 400 nanometers. So if we plug that in here, we'll get 1/2 times 400 nanometer is equal to double the thickness. So that's 200, and if you divide by 2 here, you'll get 100 nanometers, which is answer choice 1. So you can also kind of think of this as you need this wave to come back in the same phase as the reflected one. So remember that when a wave is reflected on a surface that has a higher index of refraction than it came from, it's changed its phase by 180. So if you want to think about it in terms of right when it hit, it was at a maximum, now the reflected will be at a minimum. So you want your wave that went through and then came back to also be that. So you want it basically to go half a wavelength more than what you started. That's where this half comes from. And it travels the thickness twice, which is why there's 2t. So if you have this equation, these problems become pretty simple like that. Remember that if you want destructive interference, the only difference is that you don't add the 1/2 here. You just have an m lambda n.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.